So next we are going to discuss about the subtraction for two complex numbers z1 and z2. Similarly, let us choose two complex numbers a1 plus ib1, z2 equals to a2 plus ib2. Subtraction. So we have to do z1 minus z2. Actually, in case of real number, if we write two real number like a and b, then we can say a greater than b or b greater than a. This type of property, greater than less than property, hold in case of real numbers. Then a minus b, if a greater than b, then a minus b will greater than 0. If b greater than a, then b minus a greater than 0, a minus b less than 0. This type of thing holds in case of real number system. But in case of complex number system, we cannot say z1 greater than z2 or z2 greater than z1. So this type of greater than less than thing doesn't hold in case of complex numbers. So if we if we subtract z1 minus z2, then we cannot say that z1 minus z2 greater than 0 or less than 0. Okay, so let us do the subtraction. So the same rule will apply as we did in the addition property, like a1 plus ib1 minus a2 plus ib2. So the rule for the addition was add the real part and add the imaginary part. So similarly here we will do the same thing, subtract real part plus I into subtraction between the imaginary part. Next, for example, suppose minus 7 plus 3i and z2 is minus 5 plus I. So you have to find z1 minus z2. So it is minus 7 plus 3i minus 5 plus I. So subtraction between the minus of a2. So a2 is minus 5. So minus of minus 5. Subtraction between the real parts plus I into the imaginary part. Here it is 3 minus the imaginary part is here 1. So it becomes minus 7 plus 5, that is minus 2 plus 2i. So you cannot say minus 2 plus 2i is greater than 0 or less than 0. This type of thing doesn't hold in case of complex numbers. Now we are going to discuss the properties of the complex set under the sign subtraction, like we did in the case of addition, that it's closure, the complex set is closure under the addition, then it is associative, commutative, then we found the identity, additive inverse. So similar thing we are trying to see in case of subtraction also. So as we have seen in the previous case, that z1 minus z2 is a1 minus a2 plus I into b1 minus b2. So we can easily write it in the form a plus ib, and as we know that every a plus ib form number is the complex number, that it belongs to the set of complex numbers. Therefore we can say set of complex numbers is closure under subtraction. That means if I choose any two number from the set of complex numbers and we subtract them, then we will again get another complex number. So it is closure under subtraction. Next, let us check the commutative property. That means whether z1 minus z2 equals to z2 minus z1 or not. Okay, so we can see from above that z1 minus z2 is a1 minus a2. Now if I find z2 minus z1, then this will be a2 plus ib2 minus a1 plus ib1, which is nothing but a2 minus a1 plus I into b2 minus b1. But z1 minus z2 was a1 minus a2, here it is a2 minus a1. Imaginary part was b1 minus b2, here it is b2 minus b1. Therefore we can say z1 minus z2 is not equals to z2 minus z1. So that means the subtraction property is not commutative, or sorry, the set of complex number is not commutative under the sign subtraction. Next, check the associative property. So it's better to choose some examples and we will show that similarly the associative property doesn't hold, because associative property holds means is true for any complex number. If I choose z1 equals to 1 plus I, z2 equals to 3 plus I, and z3 equals to minus 5 plus 7i, and if associative property holds, then z1 minus z2 will equals to z1 minus z2 minus z3. So this will hold for any complex numbers, but we will show that this doesn't hold in case of subtraction. That means this is not equals to this. So let's do it. So first find z1 minus z2. That is 1 plus I minus 3 plus I. So subtraction between the real parts plus I into subtraction between imaginary parts. So 1 minus 1. So it becomes minus 2 plus I into 0. Next, z1 minus z2 minus z3. That means minus 2 plus 0i minus z3. z3 is, the subtraction is minus 2 minus of the real part, that is minus 5, plus I into 0 minus 7. So it becomes 5 minus 2, 3, and here it is minus 7i. So z1 minus z2 minus z3 is 3 minus 7i. Now let us find the right hand side. So keep it as it is. Now find the right hand side. That is, first find the bracket term z2 minus z3. So z2 minus z3, that is 3 plus I minus 5 plus 7i. So same thing, 3 minus of minus 5 plus I into 1 minus 7, that is, it is plus 5 plus 8, and it is minus 6i. So next is z1 minus z2 minus z3, that is, z1 is 1 plus I minus 8 minus 6i. So the same thing, 1 minus 8 plus I into 1 minus 6. So the answer will be minus 7 plus 7i. Therefore here it is minus 7 plus 7i. Here we are getting minus 7 plus 7i, and here we are getting 3 minus 7i. Therefore not equals to z1 minus z2 minus z3. So if any property is not true for at least one number, then we can say the property doesn't hold for the whole set. So that means the associative property doesn't hold for the set of complex number under the sign subtraction. Next, we will discuss about the multiplication between two complex numbers. Multiplication two complex numbers. Multiplication of two complex numbers. So similarly, take z1 equals to a1 plus ib1, z2 equals to a2 plus ib2, where a1, b1, a2, b2 all belongs to the set of real numbers. Now we have to find z1 into z2, z1 dot z2. So write it as a1 plus ib1 into. So as you can remember that whenever we are multiplying two algebraic terms, like suppose x plus 2y and 3x plus y, or 3x plus 5y. So what we do? We first take the multiplication of this one with respect to x plus then 2y into the 2y into this one. So that means first take multiplication of 3x plus 5y with x plus 2y into 3x plus 5y. So that becomes 3x square plus 5xy plus 6xy plus 10y square. So it is 3x square plus 11xy plus 10y square. The same rule will apply in case of complex numbers also. That means here we will first multiply this complex number with respect to a1 plus ib1 into again this complex number. So let's do it. So it becomes a1 into a2 plus ib2 plus ib1 into a2 plus ib2. So multiplication a1 a2 plus I into a1 b2 plus I into b1 a2 plus I into I is I square and this is b1 b2. So what we did in case of algebraic system, we take the x terms all together, y terms all together and xy terms all together. The same thing we will do here. We will take the term along with the imaginary unit I all together and other terms all together. So a1 a2 plus, so take common I, it becomes a1 b2 plus b1 a2 plus I square is, you can remember, I is root under minus 1 and I square is minus 1, so we can put here minus 1 b1 b2. So take the term without I altogether, so a1 a2 minus b1 b2 plus I into a1 b2 plus b1 a2. So this is the form when we multiply two complex numbers. So let's take an example. You can keep remember this term or you can direct multiply by the given form, like z1 equals to 1 plus 3i, z2 equals to minus 7 plus 9i. So you have to find z1 z2. So if you can remember this form, then just put the values. That is a1 is 1, a2 is 7, minus b1 is 3, this is 9, plus I into a1 b2, that is 9, and b1 a2, that is 21. So it becomes 7 minus 27 minus 20, and this is plus 30i, or you can direct multiply like I did to find this formula, that is 1 plus 3i, 7 plus 9i. So direct multiplication, 7 plus 1 into this plus 3i into this, that is 7 plus 9i plus 21i plus 27i square. So 20 I square is minus 1, so it is minus 27 plus I into, so I should write it as 29 plus 21, so it becomes minus 20, becomes plus 38. Okay, so this is the rule how we can find the multiplication between two complex numbers. Next we will check the properties. We'll check the properties of complex set of complex numbers under the sign multiplication, and we'll find the multiplicative identity, multiplicative inverse, all those things as we did in the case of additive addition. So if I have given two complex numbers, then we know from the previous case that multiplication will be a1 a2 minus b1 b2 plus I into a1 b2 plus b1 a2. So this is of the form a plus ib. So as we know that any number of the form a plus ib belongs to the set of complex numbers. Therefore the set of complex number is closure under multiplication, and you can easily check the associative and commutative property under multiplication sign, that is z1 into z2 z3 is same as z1 z2 into z3, and commutative property is, this is associative property, that is z1 into z2 is same as z2 into z1. Now I am going to discuss about the multiplicative inverse and multiplicative identity. So first let's have a look over the multiplicative identity. So as I said in case of addition, that additive identity means if I choose any number x and add any number y with x, then I will again get x. So what should be the value of y? The value of y was 0. That means x plus 0 equals to again x. So same thing will happen in case of multiplication also. That means if I choose any number x, then what should be multiplied with x to get again x. So in case of real number, it is very easy to say, that is the value is 1. That means x into 1 is x. So this, if I choose a number x from a real number set, then x into y will be x. Then is a y is called the multiplicative identity, and it's easy to say that y is 1 whenever x not equals to 0, because x equals to, in case of x equals to 0, the additive is multiplicative identity is any number, because 0 into suppose 2, this will again give the 0. So whenever x is not equals to 0, okay. So as I said that any number, any real number can be expressed in the form of complex numbers by taking b equals to 0. That means 1 can be written as 1 plus 0i. So if I choose a complex number z1, and if I multiply 1 with it, so it will again become z1. So that means if I choose z1 and multiply 1 plus 0i with it, it will again become z1. So we can say that multiplicative identity of any complex number is 1 plus 0i. So just make 1 in the, just change the real one in the complex field, that is 1 plus 0i. Next we'll see multiplicative inverse. So let us remember that when we are talking about the additive inverse, then what was the definition? The definition was, if a given number x and we have to find the additive inverse of x, then add any number y with x to get the additive identity. That means if I have a number given x, I have to add some another number y to get the additive identity, that means 0. So it's easy to say that y will be minus x. The same definition holds in case of multiplicative inverse also. That means if I have given number x, we have to multiply some another number y to get the multiplicative identity again, that means 1 again. So it's easy to say y is equals to 1 by x whenever x not equals to 0 and x belongs to the set of real numbers. The same rule will apply in case of complex numbers also. Suppose I have given a number z1 equals to a1 plus ib1, then let z2 equals to a2, or start with a normal a plus ib. z1 equals to a plus ib be a given complex number. Let z2 equals to c plus id is the multiplicative inverse of z1. So by the definition of multiplicative inverse, we get z1 into z2 will be equals to 1 plus 0i. So that means a plus ib will be 1 plus 0i. So we can easily multiply these two complex numbers. So it becomes AC minus BD. You can check from the form of the multiplication of two complex numbers. This is AD plus BC equals to 1 plus 0i. So equating two complex numbers by equating their corresponding real parts and imaginary parts. This is 1. This is 0. Now we have to find the values of C and D from these two equations. So this is very easy to find by elimination method. Here the unknowns are C and D. Here also C and D. Let's write in this form: AC minus BD equals to 1 and BC plus AD equals to 0. This is number 1, number 2. From equation number 2, equation 2 gives C equals to minus AD by B. Okay, take AD in the right side, minus AD by B. Now put C equals to minus AD by B in equation number 1. So putting C equals to minus AD by B in 1. So it becomes A into minus AD by B minus BD equals to 1. So it becomes minus A squared D. Now take the LCM B. So it becomes minus A squared D minus B squared D equals to 1. So take minus D common. It becomes B by A square plus B square. That means D equals to minus B by A square plus B square. So by putting D here, we will get the value of C. So the value of C is therefore C equals to minus A by B into minus B by A square plus B square. So B cancel and minus minus plus, so it becomes A by A square plus B square. So the C plus ID takes the form A by A square plus B square plus I into, and D is minus B by A square plus. So this is the form of multiplicative inverse whenever complex number A plus IB is given. So let's take an example. So now let's take one example for multiplicative inverse. So Z1 equals to minus 7 plus 5i, and I have to find the multiplicative identity and multiplicative inverse of Z1. So as we all know that multiplicative identity is fixed for any complex number, that is 1 plus 0i. So multiplicative identity is 1 plus 0i. So next, multiplicative inverse. Multiplicative inverse. So as I discussed that if Z1 is of the form A plus IB, then its multiplicative inverse will be A by A square plus B square plus I into minus B by A square plus B square. So just choose A and B from the given complex number. So in case of Z1 equals to minus 7 plus 5 by multiplicative inverse will be minus 7 by 7 square plus 5 square plus I into minus 5 by 7 square plus 5 square. So it becomes minus 7 by 74 minus plus minus minus I into 5 by 74. So these are the all how we can find the additive inverse, additive identity, then multiplicative inverse, multiplicative identity, then subtraction between two complex numbers. Again, we saw in this video how to equate this, two complex numbers, that is by equating their corresponding real parts and imaginary parts. So in the next video, we are going to discuss about the conjugate property of complex numbers, then modulus of complex numbers, how to find the modulus of complex number. Then I will discuss about the division between two complex numbers. So please like and subscribe this channel. Thank you.